Here's a tutorial for predicting reactions. We had 5 basic categories. The first one is synthesis, and yes, you are expected to recognize the type when you see it because they have some very distinctive points to them. For instance, if I have only 2 chemicals here, I don't know what else to do except put them together. If you think of them like Legos and they're already apart, you can't take them apart again. The only change you could do would be to put them together. So I'm going to take this and put them together, and I'm going to need my periodic table and ion chart. And on number one, what I have is a metal and a non-metal. I know that because I find them on the periodic table, and it might take you a moment, but here they are. And so this is in my transition metals. So this is a metal. Metals go positive, and non-metals tend to go negative. So you probably want to take some notes, by the way, right? Write some stuff down. Read it through 5 times. So zinc is going to be positive. Fluorine is going to be negative. Negative what? Negative 1. Now down here, we don't know what the pattern is, so I'm going to turn this over and find my ion chart. We said it's going to be positive, so I'm going to look down here. It's alphabetical, and zinc does make sense in English. It really is. It's just zinc. And plus, you know that from the Zn is zinc. You know that from the front of the periodic table. So zinc wants to be positive 2. So what I have is zinc that likes to be a positive 2, and F that likes to be a minus 1. Now the charges have to add to 0 in any plus minus pair, so I'm going to need 2 fluorines there. And then does that make sense inside itself? Do the charges add to 0? Yes, they do. Then it needs to balance left and right. All the atoms on the left need to equal the number of atoms on the right, but they already do, and this one is done, and that is synthesis, of course. Now on this one, I have something very similar, so similar I'm going to skip it. How about this one? Barium is in your +2 column on your periodic table. Go look. Oxygen is in your -2 column. So go look at that. The charges have to add to 0, but they already do. Now, it may seem like you're done, except that when we try to balance it left and right, this has 2 oxygen and this has 1. Now, the common mistake, don't write this down, don't actually put this in, you might take a note though, is to put a 2 there just because that 2 was there. But what this would make this is -4, 2 sets of -2, and that doesn't balance out to 0 when I have it with a +2. So that would be wrong. I want 1 of each so that the charges add to 0. But I do need 2 oxygens, so I'll put a 2 in front of that, and now I have 2 of the whole set. And then somebody's kind of yelling in their mind, but now you have 2 bariums on the right and only 1 on the left, and that would be true. So that can't be correct yet. So I'm going to need 2 bariums on the left. If I have 2 on the right, I need 2 on the left, and now it's balanced left and right. These are not very difficult either. How about we do this one? Silver likes to be a +1. How would you know that? Well, you don't know it from the periodic table because it's in this transition metal section where we don't know the charges just by looking. So flip it over and find it on the ion chart. It turns out it likes to be +1. Oxygen is in your -2 column on your periodic table. That means I'm going to need a 2 here so that the charges add to 0. Now, this does get one more little step complicated because now that this works inside itself, that's fine, but it doesn't balance left and right across the arrow yet. If I put in 2 oxygens on the left, I'm going to need 2 on the right, and don't put 1 here. Don't put the 2 here because that would make the charges not add to 0. So let's put a 2 here, and now I have 2 of this whole set. That means I have 2 oxygens, but it also means I have 2 sets of 2 silvers. I have 4 silvers, and so what we have there is a 4 there. Now, decomposition is a bit of a booger, and honestly, I don't really have this entirely memorized myself. It's in the document, the guidelines or whatever that I posted next to the retake quiz on Classroom, so print that out or have it visible. And what I mean by these are, so if you have carbonates, which have CO3 -2, it produces carbon dioxide, which you should know what that is. Dioxide means 2 oxygens, and oxide compounds. And what I mean by that, and this comes up a lot, is have oxygen on whatever else is left. So you're going to have CO2 and whatever's left with oxygens. Now, there might be a 2 here and a 3 there or whatever, but X with some number of O's, and X whatever number, O whatever number, okay? So if it has SO4 and you're just breaking it down, what you get is sulfur trioxide and whatever's left over with oxygens. This with OH minuses tends to produce water, and again, whatever's left over with oxygens. And what's in the box? Well, whatever you need to make the plus minus pair have the charges add to 0 again. So this produces oxygen gas, and we're supposed to know that oxygen gas is O2 because it's in our set of 8 that have the little star, and that means they're diatomic, and when you leave them on their own with their own kind, they make pairs. So when we say nitrogen gas, we mean N2. When we say oxygen gas, we mean O2. Fluorine gas is F2, chlorine gas is Cl2, and don't forget this one, hydrogen gas is H2, and this is just an old one from a couple years ago, and I don't know why there's 2 stars. Ignore that. It's just 1 star. That 2 stars is misleading. So we have oxygen gases O2 and chloride compounds, and so what we're going to have is whatever's left over with chlorine, not oxygen. This breaks up into water and just whatever's left. And binary compounds, just 2 elements, break down into their elements. So what we have here for number 6 is something I can break down, and it doesn't match any of these. And before somebody shouts, that's a hydrate or a hydroxide. No, it's not. There's no oxygens in here. So what I have is just 2 elements, It's a binary compound, and it breaks down into their elements. So if I tore this apart and I got just a bunch of nitrogens and a bunch of hydrogens, they would form their elemental compounds. And we were just talking about that nitrogen, left to its own devices, likes to make N2, and hydrogen likes to make H2. Now, obviously, that doesn't balance left and right across the arrow. What I notice personally first is that I've got the 2-3 problem. I've got 2 H's and 3 H's, and that is going to be solved kind of like lowest common denominator, where we're going to make them be 6, because I can turn 2 into 6 and 3 into 6 by multiplying. So I'm going to put a 3 here and a 2 there and see if that gets it done. So I do have 6 hydrogens, and look, I had 2 nitrogens, but I needed 2 nitrogens anyway. And so that does balance, and of course this is decomposition. In the quiz, you need to name the type, and of course synthesis here, but I forgot those 2, but it's kind of obvious because it's in the category. So on this one, we can break these up, and what we mean really is probably we cook them, we heat them really hard, and we're going to tear these apart. Now metals, note to self, just like to be the metal. It's just the metal, it just sits there, it's charged 0. If you want to put a little 0 there, I guess you can. It doesn't super help, but if you want to, I guess there's no rule that says you can't. And then oxygens are going to get torn off, and we just said that when oxygens are by themselves, they like to make O2. And of course, it's decomp, isn't it? So then we got to make it balance across the arrow, and 2 doesn't match 1, so there must be a 2 here. And that makes 2 calcium on the left, so there must be a 2 here. And I'll remind us that one of the ways to double check your balancing is to ask yourself, do I have all even numbers? Because that would be bad. Something would be wrong if you have all even numbers, but we don't because there's an invisible 1 right there. For this one, I'm going to need to check my rules, and it says sulfates produce sulfur trioxide and oxide compounds. So I'm going to get sulfur trioxide because of this, right? And oxide compounds. So what's left over that I haven't used? The hydrogens. And when you put hydrogen with oxygen, it's going to make water. And so then it needs to balance left and right. But you know what? It already does, doesn't it? And of course, it's decomp. Mercury and oxygen, and mercury is a metal. You go find it on the periodic table. It's in the metal section, so mercury. And when we tear oxygens off, we make O2, don't we? And this is a binary compound, just 2 elements. And then 2 oxygens over here. I mean, I need to put a 2 here. That makes 2 mercuries, and that makes 2 there, and decomp. This has carbonate in it, which is my first one here, and it says it produces carbon dioxide and oxide compound. So what's left over? The calcium, right? Calcium with oxygen. And look on your periodic table, this is a +2, and this is a -2. And the charges have to add to 0, but they already do. And then we have to balance it left and right, but you know what? It already is. So the coefficients in front are 1, 1, 1. 1 calcium, 3 oxygens. Yep, it does. So here's another one with carbonate, and we get CO2, we said, and oxide compounds of whatever's left over. Now, aluminum is a metal, pretty obviously, and it sits here, and it really does like to be +3. Now, remember, we said once you get off the stairs, these rules don't really apply. Like, don't go saying, oh, bismuth is a -3. Not really. Of course, these don't usually come up here. And I will point out that this column here, I get kids asking me, so that's +4 or -4? It's kind of neither. It doesn't really do plus minus. And then some kid says, but tin and lead are metals, and you said they're plus. Right, they are, but they're not always +4. Go look at your ion chart to find out your possibilities. But aluminum does very much like to be +3. So if I'm going to put aluminum, that's what's left over, with my oxygens, I have a +3 thing and a -2 thing. And just like we talked about with our previous setup, where was that, about 2 and 3, it was here, if I have 2 of something and 3 of something, I have +3 and -2. I'm going to need to make these meet at 6, +6 -6. So I'm going to have 2 of these and 3 of those, and then I have +6 and -6. Don't add them, multiply them. Now this adds up to 0 charge inside itself, so that's good. And they told me CO2, so that's good. Now I need to balance it left and right, and I don't think it does yet. Now I actually got myself turned around on this, and I realized that I skipped something. I skipped the point that there are 3 carbons, which is a big clue. So there have got to be 3 carbons there. Now that gives me 6 oxygens, plus 3 is 9. And the 2 aluminums match there, and there you go. That's how you wiggle out of that one. And of course, it's decomposition. Barium hydroxide, we said hydroxides produce water and oxide compounds, so water. And oxide compounds of whatever's left over, so what's left over we didn't use is the barium. Barium on your periodic table is in the +2 column. Oxygen is in the -2 column. And the charges have to add to 0, but they already do. And then it needs to balance left and right, but you know what? It already does. Decomposition. Chlorates produce oxygen gas and chloride compounds. So oxygen gas and chloride compounds. Whoops. So what's left over that we didn't use is magnesium. And look on your periodic table, that's in your +2 column. Chloride's in your -1 column. The charges have to add to 0, so there's a 2 there. Now, how many chlorines did I have on the left? 2. How many oxygens do I have? 6. Well, this is 2, so let's try a 3 there. And 1 magnesium. Yep. 6 oxygens, 2 chlorines, 2 chlorines. You know, that balances out decomposition. So for single replacement, what we're going to do is take the thing that is single, and we're going to substitute it in and grab one of the partners. Now, in these cases that I've given you here, they're all metals, and so they're all going to be positive, and they're going to grab a negative. So they're going to replace the other positive thing. So what it's going to do is kick this out. So this is going to be a positive, and this is going to be a negative. These are our groups we have here. If you look on your ion chart, you hit pause and go look at your ion chart. This is bromate, it's -1. Now, if that's -1, we've got 3 of them. Okay, we're going to have 3 of these in the end, or some way or another, right? So sodium on your periodic table, go look, is in your +1 column. Bromate is in your -1. Sorry, it's not a section, is it? On your ion chart, it's -1. The charges have to add to 0, but they already do. And the iron comes off, and we said that when metals come off, they just sit alone, and you can put a 0 there if you like. It doesn't really help. Now we got to balance this. How many bromate groups do I have on the left? Just 3. And don't put a 3 here, because that would mess up the plus and minuses, adding to 0. So let's put a 3 here. But that made 3 sodiums. Yes, it did. So let's put a 3 here. And then one iron, yeah, I think we're done, and single replacement, of course. Zinc, we mentioned earlier, likes to be a +2. So when it grabs something, it's not going to grab this, it's going to grab the thing that's negative. And then somebody says, well, how the heck would I know that that's negative? Well, H is often by itself. Go look, maybe this is a group on your ion chart, and it is. And you said zinc is on your ion chart as a +2, and SO4 is on your ion chart as a -2. So that matches, and that because the charges add to 0. And then hydrogens get kicked out, and we said that hydrogen has that star on the version of the periodic table at least that I put out there, and that means that it's diatomic, and it likes to pair up when they're all by themselves. So we'll do that. And then it needs to balance left and right, but you know what? It already does in that single replacement. Scandium. You know, scandium is rare enough that I forget, and scandium is not in a portion of the periodic table that tells me what its charge is. So let's flip this over. And scandium likes to be +3, apparently. Okay, +3. And if it's positive, it's going to grab a negative. So scandium is a +3. Note to self, it's going to grab the negative there. ClO3, which is a -1, because I looked it up on my ion chart. You can hit pause and go look that up. And the charges have to add to 0, so I guess I need 3 of those. And what comes shooting off is the cobalt, and we said metals by themselves just sit there by themselves. So now I got to balance this left and right, and this is 3 chlorates and 2 chlorates. We've got that classic 3-2 problem. So I'm going to multiply this by 3 and this by 2. And now I have 2 sets of 3 chlorates and 3 sets of 2 chlorates. So that's 6 over here and 6 over here. Now that makes 2 scandiums on the right, so I need 2 on the left. And I remember I made this 3 here, so that's a 3 cobalts on the left, so 3 on the right. And you might double check that, but also you might ask yourself, do I have all even coefficients? And I don't, do I? So that's a good sign. And single replacement. I'm going to go on from there. Double replacement is like super single replacement. We're going to trade both partners. That's why it's double replacement. Ba is a +2 on your periodic table. It's going to grab something, and for crying out loud, it's not going to grab this. This is way, way wrong, and I did catch somebody doing something like this recently. That would be wrong because positive doesn't attract positive. I don't think they checked into that when they put their answer. So positive is going to grab a different negative. So this is going to grab this, and look at your ion chart. CO3 is carbonated, it's -2. The charges have to add to 0, but they already do, so let's leave that. And then sodium is in your +1 column on your periodic table, and it would grab Cl. Now here's the trick though, I get a lot of this answer. I'm going to do this wrong. I get this. Well, that's not right, because chlorine, go look at your periodic table, is in your -1 column. And that would mean the charges don't add to 0. So what we're going to need is just one of those. And then kids are saying, but it was diatomic. Diatomic is for when they're on their own, by themselves with their own kind. And it's not. It's with the sodium. So that now the charges add to 0. And then somebody, of course, could say, but there were 2 of them. Yes, there were. So you're right. So let's balance it across the arrow, left and right. 2 chlorines makes me want to put a 2 there then, but that made 2 sodiums. You're right, but I already needed 2 sodiums, huh? So we could double check it, but that's right, and that's double replacement. So I could take the aluminum. Remember, we said aluminum likes to be a +3. You can look at your periodic table. It would grab a different negative. Do not put it with the H. It would grab the negative set of PO4. If you're not sure that that's a group, go look on your ion chart and see if it is. And it is. PO4 is phosphate. It's a -3. So that was a little lucky. This already balances to 0, so let's leave that alone. And let's make another +- pair. So H is my plus now on this one. And SO4, go look it up on your ion chart, is SO4 is sulfate -2. Well, that doesn't add up until we put a 2 there, and now the charges add to 0. And then we can start balancing it. What's out of place? Well, let's see, the aluminum. You know what? I'm going to do the sulfate, I think, first, because that's a bigger problem. Maybe 3 of these and 1 of those. So if I put a 3 there, and that makes 6 hydrogen. Well, that makes me want to put a 2 there, so I have 2 sets of 3 hydrogen, and that makes 2 phosphates, which makes me put a 2 there, but I already needed 2 aluminums anyway, so that's good. So it all works out. You can double check it, of course. The first thing you might ask yourself is, do I have all even numbers? And I don't, because I have 1 and 3. How about we do 22 because it's a little more complicated. NH4 is a positive group, and it's the only positive group I can think of. And if you get a little confused, look at your ion chart, right? Because I get kids who think it's N and H, and these are separate positives. Well, did you look at your ion chart? Because I don't think they did. I admit it's a little confusing because it's not under N, it's under ammonium. And I know that sounds like an element, and I know that's confusing. All I can say is I didn't do it. So keep looking for NH4. And it's +1. So if I use it as a +1, it's going to grab a different negative, and this is hydroxide on your ion chart, and it's -1. The charges had to add to 0, but they already do, so let's leave that alone. And then barium is in your +2 column. It's going to grab a negative, it's going to grab Cl, and Cl is in your -1 column. Well, that doesn't add up to 0 on the charges unless I do that. And then we balance it left and right, and we're not done because I see that I have 2 hydroxides and 1 hydroxide, so I'm going to need a 2 here. But that made 2 ammonium groups, so I need a 2 here. And that made 2 chlorides, but I already needed 2 chlorides, so that is a good sign for me, and I can double check it. And do I have all even numbers in front? No, I don't, because I have 1 and 1, so that's good for me, double replacement. Okay, let's go to combustion. This is the one that gets usually the hardest, and I am expecting you to know that the products are carbon dioxide and water. So it's carbon dioxide and water. That's a pretty easy memorize it item though. The difficulty often is in the balancing. So I have a really big recommendation. Leave the oxygen to last. It can be a real booger if you don't leave that to last. So I would do carbon, hydrogen, oxygen. Carbon makes me want to put a 10 there. 22 hydrogen makes me want to put an 11 here. Here is the really common problem with this one though. When we go to the oxygen, 10 times 2 is an even number, is 20. 11 sets of 1 is 11. When you add an even number and an odd number, you get an odd number. So right now, on the right side, the oxygen is odd, but on the left side, it's got to be even. And so I call that the even odd problem. You cannot multiply an even number to be odd. This is never going to work unless you completely cheat and put something in a half, and you can't do that. You really, really can't. And not because we're trying to be mean, but because in reality, you don't find 01, you find 02. There's basically no such thing as 01. So you're not going to find any. So saying, oh, I use, something and a half, 17 and a half or whatever will not happen. It won't actually happen. So I know it works mathematically, but we're trying to represent reality here, and you can't find that. So I would take a note. When you hit the even odd problem, go double everything you just did. Or if you haven't done anything, go double the thing that's odd and you'll still get there. So let's double everything we just did. Let's make that a 20. Let's make this a 22. And the thing that's hard to remember is that we left an invisible 1 right here. So let's put a 2 here. Or you should be double checking and you should say 20 carbon puts a 2 here. So 2 sets of 10. Okay, so 20 carbons, yep. 44 hydrogens, yep, 44 hydrogens. Okay, now my even odd problem I think is solved because I got even and even. How many oxygens though do I have on the right side? I have 20 sets of 2 is 40, and 22 sets of 1 is 22, and that is 62. So if this has got to be 62 here, what number goes here because they only occur in pairs? And the answer is 31. And then you can double check it, but also again, one thing to ask yourself is, do I have all even numbers for coefficients? And I don't, because 31 is odd. How about 26? Carbon dioxide and water. One carbon. Okay, 4 hydrogens. Let's try a 2 there then. And 4 hydrogens. Now, we have a different version of even odd here because this is even and this is even, but you know what? Even plus 1 is always odd. So let's go back and double what you just said. We effectively said let's leave a 1 here. By not doing anything, we left a 1 there, so let's put a 2. By not doing anything here, we said let's leave 1, so let's put a 2. And instead of that, now we get a 4. And double check, did we really mean 4? This is 4 times 2 is 8. 4 sets of 2 is 8. Okay. Now, how many oxygens are on the right side? 2 sets of 2 is 4. 4 sets of 1 is 4. And that is 8. So on the left side, I need 8 oxygens. And the thing that I have forgotten before and is easy to forget is there are already 2 of them here. So this does not need to turn into 8. It needs to turn into 6, which means there's a 3 here. And that's a good thing because remember we said you can't have all even numbers. Something is wrong if it's all even numbers. And if I forgot this and I said this needs to be 8, I would put a 4 there, and then I would have all even numbers, and that would be an indicator that something is wrong. How about we try 27, carbon dioxide and water. So this 12 makes me want to put a 12 here, and of course on these combustion ones you do a lot of erasing, so don't get weirded out by that. 22 hydrogen makes me put an 11 here. Oxygens. This is going to be an even number because even plus even is even. But even plus odd is odd. So I have even oxygens and odd oxygens. And we said when you hit that point, go back and double everything you just said. 24, 22. And don't forget that by leaving this blank, we were leaving it as 1. So let's put a 2. Let's double check that. 24 carbons, 44 hydrogens. Yep, 44 hydrogens. So how many oxygens are on the right? 24 sets of 2 is 48 plus 22 is 70, right? Now, I need 70 on the left, but here's the thing, 24 of them are already here. So what we need here is 70 minus the 24 that are already there, and this would be 50, so it's 4 less than that, so it's 46. Yep, 46. This needs to turn into 46, but it occurs in pairs, so we'll need half as many pairs. That's a 23.